That was yesterday, and yesterday's gone. We walked together hand in hand, a smile and miles of golden sand. But now it's over and done, 'cause that was yesterday, and yesterday's gone.
We at Intel Corporation think we have something new under the sun. Something important for people concerned with the design of random logic systems. A new development by Intel allows you to build complex random logic systems with just a few standardized LSI devices, at the same time as you retain the ability to do truly proprietary systems design. This new approach uses an inexpensive digital computer, micro-programmed by you, to replace the MSI gates, flip-flops, and other components formerly necessary to build random logic systems. These tiny digital computers are built from standard LSI components in regular 16-pin DIP packages. They bring the features of the mini-computer to the builder of small and medium-sized systems. Intel's system gives you more flexibility in your original design, and you're able to save time and effort and produce systems at lower costs. The principle has already been proven. Designers have found mini-computers easier to use and more flexible than large hardwired logic systems. Now, with Intel's alternative, Intel brings the power of the general-purpose computer to the designers of smaller logic systems. The MCS4 microcomputer set is a family of 4 standard LSI chips with which you can build any number of powerful, proprietary general-purpose computers. The heart of the system is the one-chip 4004 CPU. You use only one of these 4-bit CPUs for each system. It performs control and data processing functions under the guidance of the microprogramming you build into the read-only memory. The 4001 ROM acts as the personality of the system and holds your microprograms by means of a customized metal mask. To make prototyping easy and inexpensive, you can simulate the operation of this 4001 with our 1701 field programmable and erasable prongs. The 4002 RAM reads and writes data, and the 4003 shift register is used for I/O expansion. The smallest computer you can build costs less than $50 and is composed of 1 CPU and 1 ROM. The largest system you can build without adding extra logic consists of the CPU, 16 ROMs, 16 RAMs, and any number of shift registers. This is equal to 4,096 8-bit bytes of read-only memory and 1,280 4-bit bytes of random access memory. Since the personality of the MCS4 is determined by your instructions in ROM, you can make significant modifications of machine characteristics simply by changing ROM programs or by adding or taking away ROM packages, generally without changing the wiring or circuit boards. The modular nature of the MCS4 keeps you from getting caught with expensive custom circuits which won't allow your next system's updating. Microprogramming eliminates much of the long development cycle required for systems design, resulting in lower costs and systems which are easily changed or updated. So, with the MCS4, you can construct proprietary designs from just a few standard parts and have the ability to easily expand or change your systems at a later date, all while you have tremendous design flexibility. Microcomputers can be used almost anywhere to provide random logic functions such as in process control, numeric control, elevators, and highway and rail traffic controls. They're easy to use in computer peripherals, such as keyboards, displays, printers, readers, and plotters, and are an inexpensive way to create intelligent terminals. The MCS4 is also ideal for billing machines, accounting machines, cash registers, and other point-of-sale equipment, anywhere you want to decentralize computer operations. Smaller configurations of the MCS4 are suitable for dedicated computers in such applications as aviation, ground transportation, medicine, and test equipment. Okay, let's see how the MCS4 is organized. The CPU is connected to the RAM and ROM memories by a 4-line data bus. The data bus allows parallel 4-bit data transfer between the devices. A sync line carries the system's timing signal generated by the CPU. Command lines send control signals to the RAMs and ROMs. The CPU controls the system. It fetches and executes instructions stored in ROM, and it contains a number of elements. A 12-bit program counter to retain the ROM address for the next instruction, program counter address stack to save subroutine return addresses, a 4-bit accumulator with carry flip-flop, 16 4-bit general-purpose registers for temporary data storage, an instruction storage register with its instruction, execution, and control circuitry, and finally a test line for sampling any external signal. The 4001 ROM contains 256 8-bit bytes of instruction storage, an address register, and a 4-line port. At the time the 4001 is programmed, the port lines may be connected as inputs or outputs. The 4002 RAM contains 320 bits of memory, organized as 4 registers of 24-bit characters each. Each register contains 16 characters which may be indirectly addressed and 4 status characters directly addressed. It also has a 4-line output port, an 8-bit address register used for memory selection, and several timing control circuits. The 4004 fetches and executes instructions using an 8-step cycle, which takes place in 10.8 microseconds. The 8 steps involve 3 for transmitting the 12-bit address to the ROMs, 2 in which 8 bits of instruction are returned to the CPU, and 3 steps for execution of the instruction. Instructions are either of 1 or 2 bytes. The powerful instruction set for the MCS4 consists of 45 instructions, providing the logic functions which replace the old method of hardwired gates, flip-flops, and other logic elements. There are 16 instructions to perform data manipulating functions such as jump, increment, fetch, add, and subtract. 14 accumulator group instructions allow manipulation of the accumulator and carry flip-flop of the CPU. 15 I/O and RAM group instructions allow you to send data back and forth between the CPU and RAM and to get data in and out of the system. Let's look at a typical instruction, the 2-byte jump unconditional. It's stored in successive words in ROM. The first 4 bits are operation code to specify instruction type. The next 12 bits form the operand, the ROM address of the next instruction to be fetched and executed. The 4-bit OPR portion of the first byte contains the jump unconditional opcode. The 4-bit OPA portion contains the high-order bits of the jump address. The second byte OPR contains the middle-order 4 bits. And the second byte OPA contains the low-order 4 bits of the jump address. Here we'll watch the CPU and ROM during the instruction fetch and execution of the jump instruction. The CPU program counter now contains the 12-bit number 240, the ROM address of the next instruction. ROM 0 contains the jump instruction in locations 240 and 241. The CPU first sends out the low 4 bits of the program counter over the data bus to all ROMs. The ROMs store this portion of the address in the 4 low-order positions of the address register. Now the CPU sends out the middle 4 bits of the program counter to all ROMs. The ROMs store these bits in the address register and can use this address to select one of the 256 bytes of data, in this case location 240. Now the CPU program counter sends the high-order 4 bits to uniquely select one of the 16 ROMs in the system, in this case ROM 0. Only the selected ROM will return data to the CPU. The program counter now has been automatically incremented by 1 to 241 in preparation for fetching the next byte of instruction. During M1, the 4-bit opcode of the instruction stored in location 240 is transmitted to the OPR register in the CPU. During M2, the second half of the instruction stored in location 240 is transmitted to the OPA register in the CPU. This value will later be used as the high 4 bits of the jump address. During the execution cycle, the CPU decodes the instruction, recognizes it as a jump unconditional, and sets a double-cycle flip-flop to indicate a second byte of instruction follows. The second byte of the JUN instruction from location 241 is similarly accessed. The program counter now has been incremented by 1 to 242, the address of the next instruction to be fetched and executed. The first 4 bits from ROM location 241, the middle portion of the jump address, is transmitted to the middle section of the CPU program counter. The second 4 bits from ROM location 241, the low-order portion of the jump address, is sent to the CPU where it is loaded into the program counter register. In this second execution phase, the 4 high-order bits of the jump address are now transferred to the program counter. The JUN instruction is now complete, and the program counter has been loaded with a complete 12-bit address A1, A2, A3 instead of the value 242. Normal instruction fetching now continues starting at this location. I/O and RAM group instructions allow the interface of a keyboard to the computer, and encoding can be done with microprogramming. The 4003 10-bit static shift register is used to expand the number of I/O ports. The interface and encoding for 7-segment displays may be done by microprogramming, and an output port may produce clock pulses for loading data into the 4003. To build your own MCS4 system, you first define the nature of your input and output operations. This establishes the number of I/O ports required. You make a flow chart and write the program in symbolic or binary language. To help you prototype systems, we can supply you with 2 special printed circuit boards, the SIM401 or SIM402. These boards contain a CPU, a bank of RAM memory, clock drivers, teletype interface, and a bank of 1701 proms, which simulate the functions of the 4001s and allow you to prove out your systems in your lab before committing to metal masked ROMs. The MP702 programmer card allows you to program the 1701s yourself, using the SIM board and a teletype. First, you plug 3 specially programmed ROMs containing the board's software package into the SIM board. You plug in a blank 1701, Then you execute the programming sequence, which reads your program from paper tape and loads it into the 1701 PROM. To check out the program, you put the 1701 into the SIM board in place of the programmer ROMs. You run the program and debug it with an oscilloscope or other instrument. Should you find an error, you erase the 1701, correct the source tapes, and reprogram it before going on with debugging. Then when the program is fully operative, you can submit your tapes to Intel for conversion into masked 4001 ROMs. Your final system can be very tiny because of the customized LSI components. The MCS4 parts are in volume production at Intel, and except for your customized metal mask of the 4001s, they are all standard parts. Our applications people will be happy to help you with building your own LSI computer system. And to help you write your program, Intel can supply a Fortran 4 simulator assembler software package. We are also producing an 8-bit CPU, which works with standard memory elements, such as the 1103, 1101, 1401, 2401, or 1301 memories. This MCS8 system uses TTL devices to interface with memory circuits and has the ability to handle larger amounts of memory and do faster data manipulation. But the MCS4 is unsurpassed for small size and lowest cost. Thank you.
For me, you were the one, but that was yesterday.